I know, yes. Alexander has a PhD in theoretical particle physics from the University of Heidelberg. In 2010, he joined the Max Planck Institute for History of Science, where he started out as a member of the Quantum History Project until 2012. After that, he was a research scholar of the Max Planck Institute of History of Science, coordinating, among other things, the cooperative project with the Landau Nobel Laureate Meeting Foundation from 2013 to 14. In 2017, he was awarded leadership of an independent Max Planck research group. Alexander has organized several workshops at the Max Planck Institute and externally, bringing together physicists, historians, philosophers to discuss the history and foundation of quantum mechanics. Now he's part of the Munich Institute for Mathematical Philosophy, and he told me, I don't know if I can say, maybe he's moving to United States in the future. Thank you very much, Alex. Please, all yours.
Yes, thank you very much for the kind introduction and the invitation. Um, it's very nice as to be able to give a talk at least in virtual Chile, and yes, as I was telling Christian, this is for me is going to be the last talk of many in this year of the Quantum Centenary, and it's a great pleasure to give that to you here from my basement in Berlin. I've got a bit of a cold. I hope you can't hear it too much, but so it's very nice that I can just do this from the comfort of my home. And so I guess the talk is aimed at being about maybe an hour, maybe a little bit less. And but since it's always, as you all know, right, this certain challenge of giving a talk to your screen, I'm very happy to be interrupted with any questions you might have, right? Just to see whether, there's questions that pop up or something that's not clear. So please feel free, to just raise your Zoom hand at any time to ask me questions you might have. And also feel free if you want to put on your cameras as you wish. That I don't mind seeing some of my audience. So right, interrupt me anytime, but I'm also available for Q&A afterwards. So then let me start with the actual talk right after these preliminaries. Since this has been the centenary of the first papers on quantum mechanics by Werner Heisenberg, Max Born, and Pascal Jordan in the summer and fall of 1925, I've given a number of talks on this topic. And one of the big challenges, right, is to really pin down, right, what we consider the core of quantum mechanics, right? And especially for like audiences, for like more popular talks, this is, I consider, a very great challenge. And I normally have this slide here as a sort of disclaimer because the physicist John Wheeler, famous among other things for coining the term black hole, he would habitually in his talks compare quantum mechanics to Merlin the magician from the Arthur mythology, who was a shapeshifter, and so too Wheeler would always emphasize how hard it is to pin down what quantum mechanics itself is really about, right? He had like this list here in one of his talks that I show here. Like, what exactly do we consider the core of quantum theory? Is it the quantization of energy? Is it about probability laws for transitions? Is it about the quantization of other quantities? Is it about like wave-particle duality? Is it about non-commutation? There's a whole list. I can go through it, but there's very different opinions about what like the core of quantum mechanics is. Nowadays, people would like add, superposition or entanglement. Entanglement, very popular these days, is like, that's the actual core of what quantum mechanics is about. And depending on, so certainly we should talk about to general audiences, right? You need to make decisions about what you want to present as the core of quantum mechanics, but also for a historical talk to a more scientifically trained audience, such as the one here, depending on what you consider to be the core of quantum mechanics, right, you're going to tell very different histories about how it came to be. And so the focus that I want to lay today for this talk, there's a number of different approaches I've been trying. I think this one might be interesting also in that it would help you think about quantum mechanics in ways that you may not have thought about it before, is to focus on one particular question, and that is, why was the theory that resulted from what we now call the quantum revolution, why was that actually a quantum mechanics, right? We know the story starts sometime around 1900 with Max Planck and his work on black body radiation, and then finds its culmination in the years 1925 to 1927 with the construction of quantum mechanics. And then after that, right, you have further developments, and in particular you have the application of this new quantum mechanics to the electromagnetic field and the development of things like quantum electrodynamics and quantum optics. But these are nowadays considered advanced applications, and our undergraduate students, right, we teach them non-relativistic quantum mechanics, the behavior of material particles, and then consider questions of radiation and fields to be advanced applications. So very much we consider the core, the theoretical core of quantum theory to be the quantum mechanics, and it's also the creation of quantum mechanics that is being celebrated in this centenary in 2025. But it was not at all clear from the outset that the theory that would result from this quantum revolution was going to be a new mechanics. And to drive that point home, I'm going to take like a very long-term, longue durée, as we historians like to call it, approach, and really look back on how quantum mechanics fits into the development of physics as a scientific discipline as a whole. So to a scientist, if we want to use that word anachronistically, in the 17th century, it would not have been surprising at all, right, that our foundational theory is a theory of mechanics, right? In the 17th century, the beginning of modern science and of modern physics, right, physics was basically synonymous with mechanics. One might even say that science was synonymous with mechanics, and a scientific explanation was to be a mechanical one, right? You would explain, this is a famous picture here on the left from Descartes, who is pictured in the lower right-hand corner, where, for example, the pain one experiences when one puts one's foot in a fire is explained mechanically, right? There is a direct mechanical connection, mechanical contact interactions moving from the fire to the foot, through the body to the brain, and we get a mechanical explanation of how the pain in this case is experienced. And this was the general pattern, right, in the early days of modern science, that everything should be understood through mechanical contact interactions. This was, of course, let's say, inspired or understandable also with the technological development of the time, right? There are great advances in mechanical engineering and machine building at the time. I have a fancy 17th century clock here. And though people had like different ideas of what matter might look like, right? The matter whose mechanical motion we are studying. So some people like Pierre Gassendi here at the bottom was thinking of individual atoms moving through a void. Descartes himself was thinking more of a continuous theory of matter, but the general idea was scientific explanations are mechanical, they're about matter in motion and contact interactions. And this was the way all through then the development of Newtonian physics through the 18th century, right? Physics was essentially mechanics. And it's only around the late 19th century that this identification of physics with mechanics and of a physical explanation with a mechanical explanation started to change and physicists were looking towards other emerging fields of physics to provide a foundation of their discipline. So in the 19th century, we have the rise of two major novel and not immediately mechanical theories. On the one hand, thermodynamics, represented here by a steam engine, and on the other hand, electrodynamics, and I'll say a bit more about why that's represented by a street lamp in a moment. But both of these theories were at least not unambiguously mechanical theories, right? There were certainly ways of thinking about them as mechanical, right? You can think of thermodynamics, of course, in the sense of kinetic theory as just being about atoms in motion, and you can think about electrodynamics as being somehow based on a mechanical ether, right? The field somehow as motion in the ether. But there were also attempts, especially around 1900, to look at these new and very successful physical theories as providing a new and different new and different non-mechanical foundation for physics. So, for example, in the late 19th century, there were attempts to really build physics not on the idea of matter and motion, but to take energy and entropy and their transformability, the transformability of energy, as the basic concepts of physics, and mechanics just as one manifestation of the transformation possibilities of energy. And more importantly for our story, and also more influentially, there was in the late 19th century, early 20th century, a real drive to establish electrodynamics and the newly emerging field concept as a new basis for physics, something that was known as the electromagnetic worldview, where no longer you had the notion of matter or atoms being the primary objects, but instead the electromagnetic field being the primary concept, and for example, atoms or electrons arising as twists or vortices within this field or within the ether. So what I want to emphasize here is that around 1900, so around the time that the quantum revolution begins, it felt rather that the importance of mechanics as the foundation of physics was waning, and people were looking towards non-mechanical foundations that could explain the universality, say, of the laws of thermodynamics, right? Things like the second law of thermodynamics, which you could only explain mechanically by invoking probabilistic argumentation that many people were not happy with. And also there were certainly difficulties, as I'm sure you're well aware, with giving an actual mechanical picture of the electromagnetic field, right? Which ultimately led to the theory of relativity. So the point is, around 1900, right, it was not at all obvious anymore that mechanics was going to be or remain the foundation of physics. And if we look at the beginnings of quantum theory, right, they too are not at all primarily about mechanics, right? What Max Planck in his early works on heat radiation was working on was the attempt to combine the two new theories of the 19th century, namely electrodynamics and thermodynamics. And his motivation was primarily theoretical. I'll say a bit more about that in a moment. But he had the good fortune that he was also getting experimental data on the problems he was interested in, because there was a lot of work going on, experimental work on heat radiation going on in Berlin, where he was at the time, primarily because one was looking for the most efficient way to illuminate the cities at night through the kind of street lanterns that it was showing. So this was the industrial drive for this work on heat radiation that Planck profited from. Because his primary interest was really to see whether, or to what extent, one might sensibly combine electrodynamics and thermodynamics, and in particular, he was looking for to combine them, especially on the strength of their non-mechanical features, right? I had mentioned earlier that the second law of thermodynamics could only be explained mechanically by invoking statistics, right? Because the microscopic laws of mechanics were time reversal invariant, so there was no way one could get the perpetual increase of entropy from them. So one had to invoke statistical reasoning, in order to explain why entropy was always increasing. But Max Planck hoped that from electrodynamics, one might actually be able to get an explanation for the second law of thermodynamics, because his hope was that electrodynamics, as opposed to mechanics, might involve microscopic, irreversible processes. The idea essentially being, while we sometimes see spherical waves being emitted from a center, we actually never see spherical waves converging to a point. In electrodynamics, this means that you always choose the retarded solution and not the advanced solution of Maxwell's equations. And he hoped that there one might be able to find a microscopic origin for the irreversibility of physics that we see in the second law of thermodynamics. Of course, this plan of Planck ultimately failed, right? And he was convinced that also in electrodynamics, the irreversibility is just a statistical phenomenon. There's nothing in the equations that actually prevents the convergence of a spherical wave to a point. But this original question did lead him to study expressions for the entropy of, expressions for the entropy of heat radiation, and to compare those expressions he got with the measured spectral energy distribution, which we see here being measured in Berlin at the time on the right-hand side. And then famously, I won't go into much detail here, then famously finding that one needs to introduce some form of quantization, though the exact way in which that was enforced very strongly developed also in the first years of the 20th century. But the essential point I want to make here is not like go into the details of how Planck arrived at his radiation law, but to point out that the starting point of the development of quantum theory was certainly not one that dealt with the microscopic behavior of matter and thus with quantum mechanics, but it was a problem within radiation theory and thermodynamics. And it goes on like that. If you look at, say, the highlights leading up from 1900 to the development of quantum mechanics in 1925, they actually mainly deal with radiation processes and light, sometimes in the form of light quanta or photons, as Einstein first proposed them in 1905 to explain the photoelectric effect, among other things, and also to explain certain features of heat radiation. And it goes on like that. In 1913, we have the development of the Bohr model, which is, of course, a mechanical model of the atom, but its main novelty actually lies in the way it describes the emission and absorption of radiation through quantum jumps. And another milestone on the way to 1925 is the discovery of the Compton effect, of the scattering of X-rays with electrons, which is again primarily viewed as an experimental confirmation of the particle-like nature of light. So what I want to emphasize here, what the main point is, that most of these highlights on the way to 1925 were about electromagnetic radiation and its novel quantum features. And this was very much in keeping with the overall state of physics around 1900, where indeed it looked like electrodynamics was on its way in as providing a new foundation of physics, and mechanics was certainly not the the up-and-coming way of looking at physics, in particular in its foundational aspects. And yet, in 1925, the theory that is constructed by Heisenberg and then also by Schrödinger in 1926 was very decidedly a quantum mechanics and was not initially a theory of radiation processes, but a theory of, in one way or another, the mechanical motion within atoms and molecules. So, how did this come about? This was, so not even like in the period immediately before the development of quantum mechanics was this clear. If we look at the years 1923 and 24, looking back a little bit earlier, the main goal of like theoretical fundamental physics in the quantum vein was to find a quantum theory of radiation, one that could somehow capture the dual nature of light, right? One had in the 19th century and with Maxwellian electrodynamics, it had been very clearly established that light was electromagnetic waves. But at the same time now, in the early 20th century, several experiments, in particular then the Compton effect in 1923, had made it very clear that light also had in some cases, could be described and had to be described as a form of particle. And this was very much the focus of theoretical physics in those years in the early 20s. Here are a picture of a few people who were trying to construct such dual theories of light in 1923-24. There's Louis de Broglie on the left, now mainly famous for his theory of matter waves, but that was really a spin-off of his attempts to construct a dual theory of electromagnetic radiation, where you would have a field and then a particle within that field that was somehow being guided by this field. Einstein was working on this too, trying to see whether one could reconcile these two, maybe by finding singular solutions of the Maxwell equation, where the singularities of the field could be understood as particles. And then there's another person here who was working on dual theories at the time. Actually, in a way, the most successful, this is Gregor Wenzel, who in 1924 writes a paper that was ignored at the time on quantum optics, again trying to find a dual theory, a wave-particle theory of light, which nowadays in hindsight we can see actually contains essential elements of what would later then become Feynman's path integral formulation of quantum mechanics. So this was very much the spirit in the early 20s, was to finally resolve this issue of the wave-particle nature of light and find a dual theory of radiation. That would be then a new quantum foundation for physics.
Sorry, what is the name of the last one? Sorry,
Gregor Wenzel is the name. Wentzel. He was in, I guess he was in Switzerland, in Zurich at the time, yeah.
And also, I didn't have very clear, the paper of Heisenberg start also by radiation, because the absorption
Good.
of atom, but
Yes.
you also start with that. Why you are saying they have like a different...
Good. We'll get to that in a moment because, okay, good. So, no, very good. So there is, right. The focus in 23-24 was very much on the nature of radiation, right? How do we reconcile its continuous wave features with its particle-like features, and trying to find some kind of theory that would encapsulate both and really thereby serve as a new foundation for what the world is made of, really, right? There had been, there are older mechanical ideas of atomism. Then in the 19th century, the field concept becomes very central to physics, and around 1900, physicists are trying to really build physics anew on the field concept, where matter becomes kind of like an emergent phenomenon. And really in this, it was clear that this could not be like the whole story, because there's this problem of the wave-particle nature of light, and this is really the main focus of the early 20s, and trying to figure out, well, fields are not the whole story. Somehow we need to bring like this quantized element into the fields, and that's what people are really trying to work out, right, in the early 1920s. And that's, of course, not addressed in then the papers that we get to with Heisenberg and Schrödinger. I'll get to that in a bit. The most successful, or let's say the most prominent theory of the nature of radiation at the time was published in 1924 by these three gentlemen here. There's Niels Bohr, his assistant Hans Kramers, and John Slater, a young American who came as a postdoc to Niels Bohr's Institute in Copenhagen in 1924 or late 1923 with some ideas about a dual theory of radiation in his luggage, and was then immediately seized upon by Bohr, the head of the institute, and his assistant Kramers, and they turned Slater's rough ideas into a paper that would afterwards be known just by the initials of the three authors. One of the first, this is of course nowadays commonplace to have like papers with three or more authors, which are then given these kinds of acronyms. BKS is one of the first, if not the first, paper to be known in this manner. And Slater was later somewhat bitter about his ideas having been seized by Bohr and Kramers, but at the time he was he at least yes, accepted it. We have like letters that he wrote to his father from Copenhagen, where he tells her that, to his father saying, "Oh, mother will say, poor little Johnny won't get what's coming to him, but I don't think that's so. If I were to publish myself, so without Bohr and Kramers, people would say, oh, another American theory. That's the way they do here." And so he was happy at the time, or at least satisfied with the idea of publishing together with Niels Bohr, who was very much still at the time, right, the leader of the young generation of quantum physicists. And so together they wrote a paper, the BKS, or Bohr-Kramers-Slater theory, where the general idea is that there are only electromagnetic waves, right? There are no actual light quanta in there. So in a way, Maxwell's equations, at least for free space, are valid. But these electromagnetic waves, they do not actually carry energy or momentum like they would in classical electrodynamics. These are just virtual waves, as they call them. And the only thing that they do is induce probabilities for transition processes in atoms. So if one of these virtual waves impinges on an atom, it will induce different probabilities for that atom to perform some kind of quantum jump. And similarly, when an atom emits a wave, this induces probabilities for that atom to also perform a quantum jump, this time from a higher energy level to a lower energy one. So this sounds like a continuum theory at first, but the particle nature of light is in a way simulated in that there are entirely discrete, entirely discontinuous processes for when the virtual waves actually lead to a transition in an atom. Then they've done their job, and they disappear instantaneously all across space, and are replaced by a new set of virtual waves that will lead to new probabilities for transitions. So there are no photons, right? There are no particles of light, but the particle nature of light is simulated by these discontinuous transformations of the virtual field as a whole. I'm giving you this very qualitatively because it is very qualitative, right? The paper by Bohr, Kramers, and Slater famously contains just one equation, which is trivial. It's just E is equal to h times nu. So this entire theory is presented in words and is more of a research program. But these are like the general ideas, and it did include one essential prediction, namely that the correlation between an emission process, so a transition in one atom, and an absorption process, a transition in another atom that is somehow mediated by some virtual waves being exchanged between the two atoms, that these correlations are only statistical. And so this is, just to emphasize it, right, this is a weaker correlation than in quantum mechanics. It essentially means it is possible, right, that an atom, some distant atom, might absorb a wave that was never actually emitted in a transition in the original atom, right? The original atom is in an excited state, it emits virtual waves, and then those virtual waves might lead to a transition in another atom, but the original atom might decide to do an entirely different transition that does not fit with the transition happening in the distant atom, and then energy conservation and momentum conservation only becomes statistical. And there is no direct correlation between emission, or no 100% correlation between emission and absorption events. So this was the main prediction, and it was disproven incredibly quickly, like within months, right? There were, through the development of the new coincidence counters, especially by Botha and Geiger in Germany, one was able to measure very precisely the correlations in competence scattering between the scattered photon or the scattered X-ray and the scattering electron. And you can see here, this is a picture from the Botha-Geiger paper, and you got perfect correlation between the two. You would never have the situation that you only got the scattered electron or only got the scattered X-ray. You got perfect correlation, thereby immediately and spectacularly disproving the Bohr-Kramer-Slater theory. And just to emphasize how big a deal this was, 30 years later still, Wolfgang Pauli, in a letter to Niels Bohr, was like making fun of Bohr, saying that there was this tradition of flagging the big pole in front of the Copenhagen Institute at half-mast on the anniversary of the date of publication of the BKS paper, because it was such a big deal and then such a quick and spectacular failure. Now, at the time and also historically, right, it was to some extent viewed as a big success for Einstein's idea of photons and light quanta, right? Bohr, Kramer, and Slater had only had waves in their theory, no particles, and the particles were just simulated through these discontinuous transitions. And so some people were talking about, Einstein's triumph, and the attempt by Bohr to get rid of photons having been a failure. But it's not like this in any way enabled a new, or promoted a different research program on the nature of light. Though Einstein may have thought more in terms of photons and light quanta, he too did not have a workable program for a dual theory of radiation. And so rather than promote theories based on photons, the failure of the Bohr-Kramer-Slater theory really spelled an end to all of these attempts to try and construct a new quantum theory of radiation. And so this central goal of physics in 1923-24 is really set aside as too difficult for the time being with the failure of Bohr-Kramer-Slater theory in early 1925. And if we now look very briefly at what happens afterwards, what happens is indeed that both of the main creators of quantum mechanics, so Heisenberg and Schrödinger, they instead move their sights away from the nature of radiation and focus instead very explicitly on the mechanics happening within an atom. Of course, as Christian rightly pointed out, with the idea of explaining, say, the observable spectrum, right, which is of course related to the emission of radiation by atoms, but very importantly, not by focusing on the actual nature of that emitted radiation and how to model that, but by focusing entirely on the atom itself. So while one could read off from Heisenberg's and Schrödinger's theories. One could read off, say, what the spectral frequencies were or what the intensities of the spectral lines were. There was no dynamical description of this emission process and no model of how the electromagnetic radiation being emitted was actually to be thought of. The equations being used were always were mechanical and based on the equations of classical mechanics, which both Heisenberg and Schrödinger drew on. Now, both of them had been very involved with BKS theory, in fact. Heisenberg had been a postdoc in Copenhagen. Schrödinger had been very enthusiastic about the BKS theory, had written a review article about it, praising its novel probabilistic features and how its great explanatory power. So they were both like BKS fans, and they used elements of the recently failed BKS theory of radiation, but now used them in the more constrained framework of the mechanics of atoms. So Heisenberg, when he constructs matrix mechanics, he uses this idea of probabilities replacing classical quantities. So Bohr, Kramers, and Slater had taken Maxwell's theory of electrodynamics and replaced the field strengths with probabilities for transitions. Heisenberg does the same thing now, only he uses probabilities to replace the mechanical coordinates of the electron in the atom rather than electromagnetic quantities. And similarly, Schrödinger constructs wave mechanics using the general idea of BKS theory to merely simulate the existence of particles. So he thinks, oh, we can do everything with waves, and the apparent presence of particles, of electrons in the atom is really just an emergent feature of the wave theory that we can simulate in a similar way as BKS had tried in their theory of radiation. So very much these grand novel ideas from radiation theory that had just spectacularly failed recently were then taken over in the creation of quantum mechanics in 1925-26. Now, of course, this is not the end of the story, because obviously both Heisenberg and Schrödinger were aware of the fact that a quantum mechanics of the atom could also not be the end of the story, right? There was still the big question about how to reconcile the wave theory of light and the new quantum experiments. There was the question of how to actually model dynamically the emission and absorption of radiation by atoms. But they took very different stances as to what role a quantum theory of radiation would play. Schrödinger was of the opinion that this quantum mechanics of the atom was basically a first approximation, and that as one worked out how, say, an atom described by a wave function actually emitted radiation, one would still very much modify this new theory. While Heisenberg early on pushed the narrative that quantum mechanics as established for the atom was already a closed scheme, and while one might think about constructing a theory of radiation for the future, quantum mechanics itself would pretty much stay the way it is and could not be significantly altered anymore. I'll discuss these two standpoints in a bit more detail in what follows, because they're essential for our understanding of 1925, not as just one more step in the development of quantum theory, but really as the point where the foundational theory of quantum mechanics is established. So Schrödinger's idea was the following. He was, as many of you may know, right, originally of the opinion that his wave function somehow really represented objects in space, and that one should in particular interpret the wave function in terms of an oscillating charge density that could then actually serve as a source of radiation using the classical theory of electrodynamics, of Maxwell's theory, basically have like an oscillating dipole, a Hertzian dipole that could emit electromagnetic radiation, and that you would now, through his wave function, have an actual model of these oscillating phenomena in the atom that led to the emission of radiation, like an antenna, essentially. And he made some progress with this, right? He was able to model the emission of discrete spectral lines, as in Bohr's atom. He was able to work out a description of the Compton effect in this way. So there was some reason to believe that he was making progress in this direction, and that one would be able to create a unified field theory, where one had a field theory of matter, Schrödinger's wave functions, combined with a field theory of electrodynamics, in a unified field theory, very much in the spirit of the electromagnetic worldview that I alluded to in the beginning, where people were expecting the field to now be the fundamental concept on which all of physics was built. We know a fair amount. I just want to show this because, to get an idea of where we actually know all of these things from, right? Here's Schrödinger had rather detailed notebooks which he kept, and which they're not very reliably dated, but one can reconstruct his thought process very well. This is like just an illustrative snippet where you see, for example, here, he's trying out how his wave function, there you see the psi for his wave function, how that might be used to construct a density. There in the upper left-hand corner, how that density would then be oscillating with the transition frequencies, and how if you had two eigenfunctions, two eigenmodes of the Schrödinger equation at the same time, you would get this kind of interference effect that would lead to an oscillation. And then you could actually calculate there in the lower part, you could calculate the dipole moment of such a atom described by the wave function, and actually calculate the emission of radiation by such a thing. And that was how he was hoping to combine his new wave mechanics with a field theory of electrodynamics. Now, there was a central problem, and that was that like the original quantum problem, so Planck's law of black body radiation, seemed to be impossible to get at if you stuck with a continuous theory of electrodynamics. And so here's just a quote from a German, it's in German because it's from a letter that Schrödinger writes to Wien. So these letters are another important source for our historical reconstruction. And what he writes is that he would be entirely hopeful if he knew how to do like a statistics, how to get Planck's law. He hopes it very much. It's not entirely impossible, he says, for after all, classical statistics is based on the equations of mechanics, and these have been changed, so maybe you can get a new statistics and get Planck's law. It's almost that would be too good to be true, he says, but he's very hopeful that his idea of like a field theory of matter and radiation might be able to lead to something. But there's now I said earlier, right, that Schrödinger was expecting that these ideas about radiation would actually lead to a modification of quantum mechanics itself. And let me just briefly explain how that would come about, right? So on the one hand, you have this idea of matter, say an electron in an atom, acting as a continuous charge distribution and emitting radiation in that way, an oscillating charge distribution. But on the other hand, if we look at the Schrödinger equation, say for the hydrogen atom, which is here taken from one of Schrödinger's papers, there we assume that we can model, say, for example, the hydrogen nucleus as a point charge, right? That's why we have here this 1 over r Coulomb potential. So there seems to be a discrepancy between the way we describe matter when it emits radiation and the way we describe matter when it interacts with other matter within the Schrödinger equation. And so Schrödinger writes in a footnote in one of his papers, he says, oh yeah, probably the Schrödinger equation is going to have to be changed, right? It doesn't really matter, he says, when we're dealing with like one very heavy object, like the nucleus of a hydrogen atom, and one lighter object like the electron in that hydrogen atom. But it will become very relevant, he says, when we're dealing with two electron systems and their electromagnetic interaction. There we're going to have to take into account that both of those are really extended charge distributions, and we won't be able to take the mechanical equations, the classical mechanical equations with like the 1 over r Coulomb interaction. We won't be able to just take them and turn them into the Schrödinger equation, but we're going to have to actually modify the equation for the wave function. And so that's how the emission of radiation is kind of like the primary thing, and that will ultimately lead us to modify the Schrödinger equation, especially, right, the paradigmatic example is two electron systems where the two electrons interact via their Coulomb interaction. There we have to take into account that these are really described by extended wave functions. And this was kind of where Heisenberg drew the line, right? Heisenberg was initially very positive about Schrödinger's new wave mechanics, right? He felt that, oh, this is a nice complementary way of viewing what I've done. It might, shed new light on the physical interpretation. But when Schrödinger then came and said, oh, but actually, what we've done here is just a first approximation, and things are going to change once we actually talk about the emission of radiation. There, Heisenberg felt that there's certainly some element there of Heisenberg being worried about this reducing the importance, like, of his big breakthrough of 1925, which would then have just been like another approximate step towards a final quantum theory, which would be based very much on Schrödinger's wave functions, and matrix mechanics would just ultimately be the linear approximation to that. But he also had like very good physical reasons to be opposed to Schrödinger's ideas, because he very clearly saw that there was no way back to this purely continuous theory that Schrödinger was hoping for. Schrödinger was like talking about, oh, we're going to get rid of all of these awful quantum jumps and return to a classical continuous field theory, and Heisenberg did not believe this. And here, this is in a letter to Wolfgang Pauli, where he writes, here now, I'm going to send you an unofficial remark on physics. The more I think about the physical part of Schrödinger's theory, his ideas about really thinking about electrons as continuous charge distributions, the more horrible I find it. And then in the end it says, I think it's actually garbage, right, what Schrödinger is doing here. Mist is the German word, which means manure or dung. Yeah. So Heisenberg was looking to counter Schrödinger's ideas. Now, one way to do that would have been to propose a different theory of radiation, right? To say, Schrödinger's ideas about continuous radiation are nonsense. Within our new quantum mechanics, I'm going to construct a different picture of how radiation is emitted, and that will be compatible with the equations of quantum mechanics that we already have, and B, it will also like fully incorporate the discontinuities that we need, for example, to explain Planck's law. But this was actually not Heisenberg's specialty. So very soon, right after his original paper in the summer of 1925, Heisenberg starts collaborating with his with Max Born, who's a professor in Göttingen, where Heisenberg is a junior lecturer. and also with Max Born's assistant Pascal Jordan, whose picture we have here in the upper right-hand corner. Historically a very problematic person, right? He goes on to write under a pseudonym these bizarre ideological Nazi pamphlets. But at the time, right in the mid-1920s, this theory of radiation was very much like Jordan's business. He had written his PhD thesis on quantum theories of radiation. He had been corresponding with Einstein about this. And when Einstein, for example, writes a letter to Heisenberg to inquire about what is going to be with the theory of radiation in your new quantum mechanics, what about photons, there Heisenberg refers him to Jordan and says, oh yeah, I have to first confer with Jordan. This is his expertise. So Heisenberg, even though he had the most at stake, right, because he was, the founding father of quantum mechanics, he did not want to venture back into a quantum theory of radiation, which other people would be working on. Instead, his strategy was to disprove Schrödinger's idea that quantum mechanics would still have to be modified. So recall that Schrödinger was expecting that the place where quantum mechanics would be modified was going to be two electron systems, right? This was when we have two charges of the same, two charged particles of the same mass interacting. Then this is where Schrödinger predicted we would see discrepancies with quantum mechanics as it had been developed so far. And so Heisenberg set himself in the mid-1920s, yes, okay, thank you. In the mid-1920s, Heisenberg set himself to studying these two electron systems and showing that quantum mechanics by itself was perfectly able to describe them. And this is one of the reasons why in this period, in the summer of 1926, he focuses on like the two paradigmatic two electron problems, namely the spectrum of helium and the hydrogen molecule, right? These are the two classical two basic two electron problems of quantum mechanics or of atomic physics. And what he finds is that yes, indeed, right? Quantum mechanics is spectacularly able to both describe the unorthodox or the unusual features of the helium spectrum, of the separation into para and orthohelium, for analogous arguments for the hydrogen molecule. He is actually officially awarded the Nobel Prize because he had predicted the analogous two different forms of the hydrogen molecule. And at the time, the Nobel Committee was very much still wary of theoretical physics, right? This was theoretical physics, still a comparatively new field, not much represented in Sweden, for example, and the Nobel Committee was very eager to award prizes specifically for very concrete experimental predictions, which is why the discovery of two forms of hydrogen is specifically mentioned in Heisenberg's award of the Nobel Prize. Similarly, also one of the reasons why Einstein never got the Nobel Prize for relativity, but instead for his equation for the photoelectric effect. So Heisenberg has spectacular success with this, right? He shows that quantum mechanics, without any kind of modifications, is able to deal with two electron problems. And then he writes that at the end of this paper, he emphasizes very strongly, he says, for me, what this investigation that I just performed, what this implies is that we probably do not need to solve the problems of radiation in order to do calculations of the spectra of atoms with several electrons, right? He's saying we have these spectra are entirely determined by quantum mechanics, and we do not need to worry about the nature of radiation or the general problem of constructing a radiation theory. And he goes on to like really emphatically press this point, saying no, quantum mechanics is finished. He coins the term of a closed theory. In a very nice letter, like in late 1926, he writes to somebody, to another physicist out of Smekal, who is pressing him about radiation. He's like, radiation theory, that's a mere detail that should not obscure how many beautiful things there are now in quantum theory, right? All of the wonderful things we can do with quantum mechanics alone, in atomic and molecular and solid state physics, without having to worry about radiation theory. He briefly works on, okay, sorry, here we go. And he very strongly pushes this point also at the Solvay meeting in 1927, where he says, well, the quantum mechanical treatment of the electromagnetic field is not yet completed, but we consider quantum mechanics to be a closed theory, geschlossene Theorie is the German term, whose fundamental physical and mathematical assumptions are no longer susceptible of any modification. So very much, the way that me and Bonn and Jordan constructed the theory in 1925 is the final version of it, and this is our new foundation of physics, this non-relativistic quantum mechanics of material particles. He tries his hand at a quantum mechanical treatment of the electromagnetic field himself. Great difficulties ensue, and it takes another 20 years, right, for a workable theory of quantum electrodynamics to then be developed in the late 1920s by people like Richard Feynman, Julian Schwinger, Shinichiro Tomonaga will all get the Nobel Prize for that. But in these 20 years, right, it becomes Heisenberg's view, well, quantum mechanics is like the foundational theory, and radiation theory is something for the future, or maybe just an application. It's definitely difficult. This becomes very strongly entrenched, and I think we still see this in the way that quantum theory is presented both in popularization and also in teaching, right, that non-relativistic quantum mechanics and its application to material particles, right, is viewed as the foundational aspect of quantum mechanics. So let me very briefly conclude by just telling you the story that I presented to you in 1 minute. So back in 1924, constructing a quantum theory of radiation was like the big question that people were working on, and that people expected the culmination of the development of quantum theory to be. But the failure of the Bohr-Kramer-Slater theory instead led people to turn to the less ambitious, seemingly, project of theories of quantum mechanics, which were developed by Heisenberg and Schrödinger in the years 1925 and 1926. One small thing to add, maybe, I think further confusion was brought in by Niels Bohr, who in a famous lecture he gave in 1927 implied that the development of wave and matrix mechanics somehow also resolved the wave-particle duality of light, right? He equated those two things, which is really, I think, has confused people to this day, because those are very different aspects of wave-particle duality. But so after quantum mechanics was constructed in 1925 and 26, Schrödinger saw this as a first step that would still be a first approximation, maybe, a theory that would still be modified once one actually developed the quantum theory of radiation, while Heisenberg, and his view ultimately won out, started pushing to consider quantum mechanics as a closed theory, fortifying this view by his successful application of quantum mechanics to two electron systems, like the helium atom and the hydrogen molecule, and thereby, and this is, say, the final twist, re-establishing, after centuries, mechanics, or a new form of mechanics, as the foundation of physics, just at the point in history where it had seemed that field theory or concepts of energy might actually replace mechanical concepts of position and motion as the foundational concepts of physics. Thank you very much for your attention.
Thank you very much, Alexander. Really nice talk. And please, we have some time for questions. You can raise your hand or write the question in the chat. I would like to start, Alexander, by a question. first, I didn't know how important was the BKS paper. I always thought was just a failure of the conservation of energy. But that paper you mentioned, they talk about the conservation of energy is only statistical,
Yes.
but in the uncertainty principle, we use the delta E. People use it's kind of a statistical way to show the energy. Can you comment on that? Is there is a relationship between the delta E in the uncertainty principle with some uh, statistical conservation of
Yes.
energy or not at all?
No. So no, they're I would say no. I mean, essentially, I mean, if we think of the energy time uncertainty relation, right? Delta E times delta T is greater than H or something like that. I mean, first of all, its foundational status was discussed um, um, a lot in this period, right? Because time is not really a so there were quite some debates about what its role was. But I think the important thing there is that there is the idea that, say, um, for each process you have a certain uncertainty in energy, right? You get like a certain spread, say, of the spectral line width, right? Because of you have uncertainties about the exact time of emission or however you want to model it, right? Um, in the BKS theory, there was really the idea that there were like lots of processes where energy was perfectly conserved, yeah, but once in a while there would be individual microscopic processes where energy was not preserved at all, right? Where
Okay.
you would basically have an atom yet performing a jump in, with energy delta E1, and then some other atom seemingly absorbing, right, the light emitted by that atom would jump up by energy delta E2, which is much greater or much smaller than the original jump of the other atom. So there would be individual processes that like blatantly and measurably violated energy conservation. And it was only if you so there was not it was not a sense that here maybe the best way to say it this way, in the BKS theory, the non-conservation energy, the energy is only conserved in a statistical average over a large number of processes. Yeah.
Okay.
While
Yes.
in the energy time uncertainty relations, energy is conserved in a time average of an individual process.
Good.
Yeah.
Yeah, we have a question from Eugenio Bogel. Please, Eugenio, you can unmute your. Uh, yeah.
Okay, thank you. Good afternoon or night, whatever it is for you at the moment.
Night, yes, very much.
Yes, thank you for your talk. Uh, your emphasis was on the radiation
Yes,
aspect of quantum mechanics. I want to take you to something that happened in parallel with this at the
yes,
end of your the period you covered, which is spin. You didn't
yes.
even mention spin.
Right.
How is related to what you just
Good,
mentioned.
good, absolutely. Yes, right. Like I said in the beginning, right, one has to like choose one kind of emphasis to tell a story. There are definitely other stories one can tell, and one of the stories that one can focus on in the creation of quantum mechanics is like unraveling or understanding the um, more complex spectra of atoms and molecules, right? The original success of the Bohr model in 1913 is to explain the spectrum of hydrogen. It gets extended to include the Stark effect, so application of electric field, and the Zeeman effect for the application of a magnetic field. So those are like the original successes, but as soon as things get more complicated, right, the Bohr atom reaches its limits. Helium is one example, but also another important example is what was called the anomalous Zeeman effect, right? And it was not at all clear how to yes, how within the Bohr model to explain this specific kind of splitting of the spectral lines in a magnetic field. So there is, of course, an entirely distinct strand of finding better and better models of the atom, right, that will explain more complicated spectra, of modeling the mechanics of the atom. This is there is this strand, and in a way, right, quantum mechanics stands in this lineage. But it was, the point I wanted to make was that it was not considered the most foundational question, right, say in the years right before. That was certainly the nature of radiation. But people were, of course, working on improved models of the atom in order to explain certain peculiar features of the spectrum. And in this context, the Goudsmit and Uhlenbeck made their proposal of the electron spin entirely independently at first of the development of quantum mechanics. This happens around the same time, but these developments are entirely independent, right? The Goudsmit-Uhlenbeck proposal of spin is still very much in the tradition of the old quantum theory and the Bohr model. And then really so I mentioned, right, that when Heisenberg goes on to apply quantum mechanics to certain problems in atomic and molecular physics, he focused then in the summer of 1926 on two electron systems, hydrogen molecule, helium atom. But actually the very first paper that he writes as an application is a paper together with Pascal Jordan, in which they incorporate the new concept of spin into the new matrix mechanics, and prove that in this way one can reproduce the splitting of spectral lines observed in the anomalous Zeeman effect. So in a way, it is really, spin is developed independently, but it becomes the first really novel application of the new quantum mechanics, is to incorporate spin and explain the anomalous Zeeman effect. Up until then, right, Heisenberg in his foundational papers, he works out the anharmonic oscillator, and then Pauli is able to reconstruct the hydrogen spectrum through a very complicated calculation. But the first novel explanation that matrix mechanics provides is by incorporating this new concept of spin, and thereby showing that it can resolve this long-standing problem of the anomalous Zeeman effect. That's maybe one interesting aside is that people initially expected the new concept of spin to actually carry much, much further than that. So the originalists, Bohr and Pauli, they expected that also the unusual features of the helium spectrum, the separation of the para and orthohelium, would also be explainable by the interaction of the two of the spins of the two electrons. And it's only then, so this is basically the first step that Heisenberg does in his two electron calculations, is to show that the spin-spin interaction in the helium atom is much too small to explain the differences in the spectrum between para and orthohelium.
Thank you, Alexander. There is a question in the chat from Jose Maria
Yes.
Espino. They say, thank you for your talk. What is the current appreciation of quantum mechanics as a closed theory in light of the ensuing development in the last 100 years? Example, Feynman and others.
Yes. So, yeah, that's of course also, well, I think it's the extent to which Heisenberg's assertion, right, that quantum mechanics was a closed theory, the extent to which that has been proven right, is quite surprising. The extent to, I think like in 1926, this was, it was not, objectively looking at the debate, right? You can see, well, clearly Schrödinger has some issues because he tries to make everything continuous, and how are we going to get Planck's law out of this? But similarly, right, it seems very, very optimistic. If you look at it from the perspective of 1926 of Heisenberg, to say, well, quantum mechanics is already finished, right? We basically have the correct framework, it can't be changed anymore. And I think the extent to which Heisenberg was proven right in that is, it would have surprised even himself, right? He was expecting that, in particular, like finding a quantum theory of radiation would actually require a revolutionary new theory, just that this would not change the quantum mechanics inside the atom. I mean, one has to, well, before I go off in a direction that may not answer your question, maybe you can, were you thinking of Feynman, are you talking more about the development of quantum field theory, or thinking more, say, about path integral formulation of quantum mechanics? I'm not quite sure what the,
Um, well, maybe I'm not a specialist in the field,
yeah,
but as long as I can understand, can we say today that it is a closed
yes,
theory?
good, okay,
Or
right. Um, so, um, So Heisenberg actually went on to develop an entire philosophy based on this idea of a closed theory, where quantum mechanics is not like the only closed theory. Like Newtonian mechanics is viewed as a closed theory, Maxwell electrodynamics is a closed theory. A closed theory being a mathematically self-consistent description of a well-delimited set of phenomena, right? So you would say, well, quantum mechanics is, may not be able to describe radiation, but within the atom, within atomic, molecular, solid state physics, it is exact and self-consistent, right? This was Heisenberg's conception. And again, right, one has to look at this generation, right? They had grown up in a world where physics was like, in a constant state of revolution, right? Heisenberg was born in 1901. His entire physics education was during the development of quantum theory. When he came to university, right, it was, the relativity theories had just been developed, right? There was the expectation of this generation was, there's just revolutions all of the time, right? And Heisenberg was thinking, well, of course the next revolution is right around the corner, yeah? There's going to be another revolution for, based, where we develop like a quantum theory of radiation. We don't know what that's going to look like, and it's going to leave quantum mechanics behind as a closed theory with its own specific domain, just like Newtonian mechanics is a closed, self-consistent theory with its own specific domain. Now, that actually did not happen, right? Because then, in the late 1940s, in the work of Feynman and others, right, it was actually possible to develop a quantum theory of electrodynamics that's more or less within the framework of quantum mechanics. There's some parts that don't fit perfectly, and the Hilbert space structure is different, but in general, it fits into and there was nothing. You would still say, oh, we have to, you have to learn quantum mechanics, and then you can, like learn quantum field theory as a specific application building up on that. So I think, in a way, the robustness of quantum mechanics, then also, as it's, yes, exactly. The robustness of quantum mechanics also with regards to, the many experimental tests of its foundation has exceeded Heisenberg's expectations, I think, even. But just like to emphasize, right, nowadays, exactly, if we think about, say, tests of quantum mechanics, and we think about tests that test things like, the Bell inequalities and how does entanglement work and these kinds of things. This was not the kind of things that Heisenberg and Schrödinger were worried about. Right? The real thing was, if they were thinking about where might the limits of quantum mechanics lie, right? Like for which phenomena might quantum mechanics stop working? They were thinking this was going to be the description of radiation, right? That's what they were discussing about. And this idea of, we need to interpret quantum mechanics, and then novel phenomena like entanglement might arise. This is something that only gradually then emerges in the late 20s and early 30s, and that we would that we would consider something like, an EPR type experiment as a foundational test of quantum mechanics, or maybe like even the foundational test of quantum mechanics. is something that really only is in the 1970s, right? Heisenberg would have said, well, that's, of course, their quantum mechanics works, right? The big question is it going to work for very high energies? Is it going to work in the atomic nucleus? Those were the things that they were thinking about as possible limits. And yeah, I think surprisingly, right, quantum mechanics, it worked more or less for the atomic nucleus, it worked for fields, and this was certainly way beyond what Heisenberg had even anticipated when he said quantum mechanics is already finished in 1926.
And also, Alexander, at the
Thank
very
you.
beginning also of the theory, Paul Dirac tried to do like a field theory, like he was from the very
Yes,
beginning. You didn't mention much about the
right.
contribution of Paul Dirac from this
Yes,
kind of radiation theory. What do you
absolutely.
think? That was like a, even before that, Feynman on all of them,
Yes,
Paul Dirac tried to do the first. And
that's right. So Dirac is really, so I had this one slide where I said, well, Heisenberg could have done two things, right? Like either show that quantum mechanics works very well within the atom for two electron systems, or develop a theory of radiation within quantum mechanics. So not something that is going to change quantum mechanics like Schrödinger thought, but using the framework of quantum mechanics and like very gently generalizing it to get like a quantum theory of radiation. Jordan was working on this in like Heisenberg's immediate vicinity in Göttingen, but actually Jordan is then beaten to the punch by Dirac, who in early 1927 publishes two foundational papers
yeah,
on the quantum theory of radiation, which at first glance look to be incredibly successful, right? They're able to explain, well, emission and absorption of radiation. They can explain dispersion and anomalous dispersion.
yeah. The
So at
spin,
first it looks like, oh, yeah, go ahead.
no, the spin also appeared naturally on the
Right. Then,
equation
of course, Dirac also extends this
to,
to relativity
to
theory, which then
relativity,
gives
yes.
the spin. But then Heisenberg and Pauli, they take up Dirac's original work and try to turn it like into a fully relativistic quantum field theory of electrons and radiation and work this out in full detail. Like Dirac gives like a bit of a phenomenological sketch. It's not fully relativistically invariant the way he formulates it. And Heisenberg and Pauli then try to put all of these like
Yeah.
starting points of Dirac together in like a series of two very long papers that they write in 1929, 1930. And in these papers, they find that, okay, so it works like to a first approximation very well, but actually, if you go to a second approximation in the framework essentially suggested by Dirac, you get horrible mathematical difficulties, right? You get most prominently, right, you get this this infinite self-energy of the electron, which you can't get rid of by simple subtractions. And so Pauli like writes like an angry letter to Dirac saying, I think you actually knew this back in 1927 already, and I hope in future publications you're going to acknowledge, that your original radiation theory is actually full of infinities. And this is what then convinces Heisenberg also to say, well, clearly like the straightforward way of constructing a quantum theory of radiation does not work. There's going to be another revolution in physics, like a third revolution after relativity and quantum mechanics. Now comes the third revolution, and that's going to bring us, bring all of this together. And what then happens in the late 1940s with Feynman and Schwinger and Tomonaga, also Freeman Dyson, is that through the development of renormalization theory, people get Dirac's original theory to work. Actually, right? They get rid of the infinities in higher orders in higher approximations and show that there is actually, without like a big massive revolution, you can actually get a theory of radiation within quantum mechanics, which of course further like establishes quantum mechanics as like this basic foundation. So in a way, thereby also, justifying what Dirac had done in the late 1920s and establishing Dirac as like one of the fathers of quantum field theory. But like in the immediate aftermath of quantum mechanics, it at first looks like this kind of straightforward Dirac approach of doing just a quantum theory of radiation using the rules of quantum mechanics and like quantizing classical theories do not work. And for about 20 years, physicists believe that this approach does not work until it's rehabilitated under the influence of like novel experimental input, right? There's the measurement of the Lamb shift
Yeah.
and of the anomalous magnetic moment of the electron. And that's when, through the development of some new concepts, but ultimately, ultimately it's viewed as a rather conservative resolution of the problem rather than the radical kind of third big revolution of physics that
Yeah,
Heisenberg was
and
expecting.
Dirac never liked it, like the
That's right,
renormalized.
Dirac never, yeah, that's
Yeah,
true.
yeah. We have one last question. If somebody has one last question before finish a short question, or if
Oh,
not, yeah,
yeah.
Jose, yes, please.
No, maybe it's not. If not, I don't. If it is within the scope of this talk, but how do you consider the search for hidden variables that occurred later on in quantum?
Yes, okay. Right. So this is nowadays, right? This the the search for the first attempts to construct like a quantum theory with hidden variables, non-local
Yeah,
ones, in the
yeah,
1950s by David
yeah,
Bohm, is
yes.
viewed very much as like a starting point for what some people have called the second quantum revolution, which
Okay.
really engages with the truly novel features of quantum mechanics, will ultimately lead us also into quantum computing and things like that. The identification of entanglement, right, as like a central feature of quantum theory. So it's viewed as something in a way, right? This new engagement with the foundations of quantum mechanics is viewed as um, a new progressive development as compared to like some like the conservative view of the Copenhagen physicists who did not believe in looking into these kinds of questions. Um, in the 1920s, right, when Heisenberg say was arguing with Schrödinger, right, these kinds of ideas to Heisenberg and Bohr and people like that, rather than being ideas that might point forward towards new research programs, very much looked like they looked very conservative, right? So they looked like, oh, these are people. For example, when we see Schrödinger trying to construct like a purely wave-based theory of the interaction of radiation and matter, um, Heisenberg is like saying, oh, this is one feels like one is transported 30 years into the past, right? As if one were back in the 19th century doing just field theory. So basically, what Heisenberg and other representatives of what one would call the Copenhagen School felt was that all of these ideas to try and um, resolve the foundations of quantum mechanics to make them look more like classical physics again, right? That was what
Yeah.
the hidden variables was reactionary, right? These were people who were not willing to accept the novel implications of quantum mechanics, what it tells us about, the limits of knowledge and whatnot. And so, in a way, it's really kind of ironic that ultimately that this search for hidden variables that Heisenberg and co would have branded as reactionary actually like leads to a development that showed the novel, non-classical, revolutionary features of quantum mechanics, like entanglement, in a far more vivid light than the original revolutionary founders of the theory had ever expected. So
I see.
it's an interesting, and somewhat paradoxical historical development.
Hmm. Thank you very
Alexander,
much.
yeah. The last question, are you able
Yeah.
to answer one last?
Oh yeah.
Sarah,
I'll
please.
try.
Yeah.
Thank you so much. It was a wonderful talk.
Thank you.
So my question is more on what's been happening since the
Sure.
1960s. How do you see the theory itself evolving, not just its application? Do you think like our main challenge today is that conceptual foundation or converging to a well-defined interpretation of quantum mechanics, what it means?
Um, so, I mean, maybe to like follow up, say, on my answer to the last question here, right? The One of the reasons why people like Heisenberg consider the original interpretation debate, right? The debate on like, to be sterile is because they felt, well, what interpretation really means for these people talking about interpretation is to find a way of looking at quantum mechanics that makes it look more classical and thus more intuitive, more palatable, more understandable, when in fact the right attitude for engaging with quantum mechanics is to accept its radical novelty and just roll with it, right? And interpreting it is basically just a code word for like trying to somehow massage it, to transform it to look more like a classical theory that we feel we understand better. And so, I think there is something to be said for that view, especially in the early interpretation debate, where it was really a lot about, just like, massaging the theory to make it look more palatable to different people. The game changer was, of course, when that interpretation debate then made contact with novel kinds of experiments, right? I mean, Heisenberg was always saying, why should we like sit and worry about the interpretation of this? It's a closed theory, also like a closed book, right? We know, people should, keep on doing atomic, molecular, and solid state physics with this, but they're not going to discover anything new fundamental. It's very much, I mean, so if you're familiar with like Thomas Kuhn's theory of scientific revolutions, right? They were like
part of mine.
Yeah, there's a famous like interview where Kuhn interviews Heisenberg in 1963, shortly after Kuhn has published his famous book, and they like really hit it off, right? Because Heisenberg's closed theories are essentially like paradigms, and people can keep on using them in their respective domain in what Kuhn would call normal science, but there's not going to be any radical new discoveries, is Heisenberg's idea, right? For that, we have to go towards new phenomena, high energy physics, nuclear physics. That was the, and so I think right there,
Black holes.
Black holes, yeah. There, the interpretation debate that, I think at times, may really have been as sterile as Heisenberg and others, may have viewed it to be, was successful by, exploring new physical domains of like really testing correlations and, working out things like the Bell inequalities and that. Now, the question is whether it will be continue to be fruitful in this way, right? I think, even the most optimistic people are not expecting any kind of EPR experiment to give you a violation of the Bell inequalities, right? I don't think that, that's really to be expected. So, those things are, so I think, and a lot of that is, has now gone over into applications, and we'll see where quantum computing will lead. That's a whole different question, but I think that's kind of like matured and become like its own also more applied field that has has historical origins in common with the interpretation debate, but is by now more or less separated from it. I think like the maybe the big open question, the new domain where maybe, right, the interpretation debate might still break new ground is the question of the quantum classical transition, right? The question of how are there natural limits to the entanglement and the superposition of systems, right? I think that's where where the interpretation debate is still, say, connected to an experimental frontier, which I think is in a way, right, the essential part, because I think at those points in history where the interpretation of it was not connected to an experimental frontier. In hindsight, of course, we can say like a certain groundwork was laid and a certain community was formed, but it was also very vulnerable to justified criticism of being a rather sterile endeavor of just reformulating a successful theory to look more like the kind of theories that, somebody with that philosophers might like, or somebody with a more classical, intuitive view of physical theories might like. I don't know, I hope that answers your question a bit.
Yes, thank you so much. Yeah, can I ask like a follow-up?
Please go ahead, yeah.
Personally,
Yeah.
How do you interpret, like, do you think we're going to go more towards like hidden variables or many world theories? I know
Right.
that there's a lot of research. I'm asking for your like personal take
Yes.
on our.
So, okay, since it's personal, I like answer it biographically. So right, as Christian mentioned, I did my PhD in physics, and then figured I was gonna, I still liked physics very much and wanted to like be engaged with it, but I wanted to like kind of look at it from the outside. And so I applied for jobs in both history and philosophy of physics. I ended up with a history job. And one of the things I've relished about being a historian and not a philosopher is to be able to stay out of the fray of these kinds of debates. The philosophers, they have violent and, bizarrely emotional debates about the interpretation of quantum mechanics. But I've just decided to stay on the margins of that. What I can say is I do have a sympathy, and that may have shown through in the answers that I gave, for the general approach that, say, Heisenberg and Bohr had, as opposed to people like Schrödinger and Einstein, and then later on David Bohm, to say that the weirdness of quantum mechanics and the way we interpret quantum mechanics is not a bug, it's a feature, right? This is where we need to go to mine the essential novelty. But I think as I was saying earlier, right, the historical paradox in a way is that they, at least in the way that we view things now, right, they were wrong about what are actually the weird features of quantum mechanics, right? They did not have like this whole idea of separation to subsystems and the kind of correlations we get there. They had not really, I think, fully seen that this was actually where quantum mechanics was at its weirdest. But I think the general idea, I am sympathetic with the idea of not saying, oh, we need to interpret this to make it fit with the way that we're able to think about things, but rather, to engage with the novelty and weirdness head on, for whatever that may mean. But as a general strategy, I do see a certain kind of conservative element in the entire idea of an interpretation, rather than, the theory telling us, here are the things that are like unambiguously new and novel. Think about these, rather than try to fit the theory into some explanatory or preconceived philosophical framework you might have. That's my evasive answer.
Thank you so much.
Thank you, Alexander, for your talk, for the question. Thank you, everybody, for staying here. And Alexander, if you come to South America, let us know.
Yes.
You know that Heisenberg got an offer from Argentina? Do you know that?
This story I do not know.
Yeah, I will send you in the chat. It's a paper about that.
Okay.
Yeah, but it's in Spanish, but they show the
Yeah.
letters, and I put you in the chat.
Yeah. Oh,
Heisenberg
cool.
got an offer, and he was almost coming, and they have a lot of exchange of letters between Argentina and Heisenberg. He was
Oh, excellent.
almost coming to South America.
Okay. Oh, I will read this. Thank you very much. I was not aware of this story.
Yeah, that's why we have some connection, Latin American connection with Heisenberg. But you are welcome,
Yes.
and your father stay here in Chile, and you come
Yeah.
here. You will be welcome here. Let me know.
Wonderful. Thank you so much. That's so kind of you. It was a great pleasure. Also, yeah, to have such a lively and interested discussion afterwards. Thank you very much.
Yeah, thank you, and thank you, everybody. It was a really nice talk. Bye, and discussion.
Bye bye.
Bye. Thank you very much.